I am Federico, and I'm here to present on behalf of all my co-authors, but especially Yiming, which has put an incredible amount of work into this project, but unfortunately, because of visa restrictions, he could not make it here to present it. So today I'm presenting OpenOptics, an open research framework for implementation and research in optical data center networks. But first, why optical data centers? So as you all know, the growth of data center traffic is reaching critical levels and appears not to be slowing down. And while this is a decade-old trend, it was highly accelerated by the new AI workloads that have been monopolized in the field. And this puts a lot of pressure on existing data center infrastructure. This is particularly exacerbated by the fact that Moore's law for electrical switches has run its course, and building packet switch fabric at hyperscale is becoming prohibitive in cost. And because of these, industry and academia alike are looking at optical data centers as a promising solution. Optical data centers integrate optical switches into a network fabric by providing high switching capacity at low cost. These are circuit switches, so they are programmed to establish direct, dedicated circuits between pairs of nodes. Like in the example, we see 3 optical switches under 3 different configurations, which result in 3 different sets of communicating pairs. And then these switches are reconfigured, for example, based on a predicted communication schedule. These are also physical layer devices, meaning that there is no queues, and data is to be buffered elsewhere, either on the host or on electrical switches. Because optical switching promises many benefits, such as low power usage, low cost, high bandwidth, and high topology flexibility, in the past 15 years, we have seen a large number of proposals on how to integrate optical switching into data centers, each with different ideas on how to schedule circuits around traffic or how and where to buffer waiting packets. However, even with all these proposals, this research area still has one major drawback, which is the high barrier of entry. Despite the very active exploration, optical architecture proposals still remain closed ecosystems, each with their own specialized hardware and then customized software. With evaluation, they run typically on some homegrown simulation and maybe a small-scale hardware testbed. And this makes research and innovation area quite siloed because software systems are tied to the optical hardware and there's a lack of unified platform for evaluation. Let's see a couple major examples. One of these is RotorNet, whose development cycle spanned nearly 10 years, from the original hardware paper presenting the rotor switch to designing the architecture, then the routing, and finally realizing it end-to-end. And this took extreme dedication, which only very few research groups could have achieved. And this very long cycle was dictated by the long integration process of optical hardware and software. This is also an area under active exploration from major players, such as Google and Microsoft. What we show here are both optical data centers, but they have taken completely different tech paths. Google operates Jupyter with slow optical switches, and then consequently has developed a dedicated stack of topology and traffic co-engineering, while Microsoft prototyped ultra-fast optical switches and has architected a fully oblivious network fabric for it. And these are architecture-specific designs because based on their choice of hardware, they had to concentrate the long-term efforts on a specific tech path. Our end objective is to lower this barrier of entry for researchers. In response, we realized OpenOptics, an open research and development framework that decouples software systems from the optical hardware, allowing them to evolve independently. Concretely, what we provide with OpenOptics is a system that enables realizing different optical architectures within the framework in a plug-and-play manner, a simple network abstraction and corresponding user APIs to model these networks, and a multiple backend support from, of course, a physical or a testbed, but also both simulation and emulation with NS3 and Mininet. And the objective is to enable easy design and testing. Particularly for groups with available physical hardware, we aim to shorten the development cycle by providing a fully built-in software stack that, for example, enables plug-and-play cross-architecture comparison using the same testbed. Or if a physical hardware testbed isn't available, we also provide single laptop emulation and simulation with Mininet and NS3. And those could be used, for example, for initial exploration of optical network implementations, but also for classroom education on the topic. And of course, now the question is, how can we achieve this? How to unite different optical architectures? So the network stack of an optical data center typically looks like this, with a foundation architecture, some packet scheduling and routing mechanisms, potentially an integrated transport protocol, and applications that may interact directly with the optical fabric. We approach the problem starting from the narrow waist of routing. So due to the dynamicity of optical data centers, routing is actually the key factor in system design. Let's consider this example to show why routing is fundamentally different than in static data centers. First, we call a specific configuration of our optical network at a given moment in time a time slice. And here we show a 8-tor topology across 3 consecutive time slices. Now, let's say our packet needs to travel from tor 0 to tor 3. There are mainly 2 ways we could do this. The packet could take a multi-hop path, going first to tor 1, then to tor 3. But it could also simply wait at tor 0 until it gets a direct circuit to tor 3 in the 3rd time slice. What we observed is that our routes change across different time slices, and that packets may choose to wait at intermediate tors. How can we express this? The main abstraction we use to enable this time-based routing is called a time flow table. This essentially takes from traditional SDN flow tables that map table entries to some routing behavior. But optical data centers have one more dimension to routing, which is, of course, time. So we augment our time flow table entries with an arrival time slice and a departure time slice. And this allows us to express the time a packet should leave the switch based on the time slice it arrived at the same switch. As in the figure, we can, for example, express the previous direct path route by setting the departure time slice to 2, so the packet will only leave towards 0 on the single direct circuit in time slice 2 opens towards tor 3. We can also use this abstraction to express something more complex, such as the previous multi-hop route through intermediate segments, which has an earlier arrival time slice than the previous direct route. In this case, a packet would start from tor 0 and gets immediately forward to the available circuit to tor 1. And there, first, it waits for one time slice, and only then is forwarded to destination tor 3 once the circuit opens up. And we can see we can express this quite straightforwardly with a time flow table. We set the arrival and departure time slice at tor 0 to 0, which immediately forwards the packet. And then we set departure time slice to 1 at tor 1 to forward to tor 3 only once the circuit has opened up. Furthermore, in order to be backward compatible with traditional flow tables, the time flow table supports also wildcard entries. In this case, it will immediately forward a packet like in a static network. The action field is also extended to support, for example, source routing, so that a packet will simply traverse the network end-to-end once it matches. And this is needed to implement some optical architectures. And now the challenge is how to realize this abstraction. As we see in the example, a time flow table entry may have the same arrival and departure time slice, so packets are simply transmitted upon arrival, like in a normal network. But it may also have a later departure time slice, so packets need to temporarily wait at a tor. So to support time flow tables, we need to re-architect the existing queuing system. At every switch port, we implement time-based packet scheduling. We use different queues, with each queue sequentially representing one time slice. And a queue is only active during its corresponding time slice. In this case, the packet for this entry arriving at time slice 0 is immediately queued to the active queue 0, and then it is sent out as the queue drains. As time goes by, time slice becomes 1, so active queue also changes to 1. If we set the packet arrives here in time slice 1, according to the table, it actually needs to depart in time slice 2. So it will be enqueued in the corresponding queue number 2 rather than the currently 1 active. And then as time goes by, it's eventually time slice 2, and the packet will be sent out as the corresponding queue starts to drain. And this system is to avoid sending packet, of course, into the wrong circuits, but also avoid head-of-line blocking. So this is at surface level how the underlying routing system works for OpenOptics, but there are actually more mechanisms for this to function correctly, so please check our paper for more details. So we have seen that actually these time flow tables are quite expressive, but at the same time, due to the additional time dimension, programming them manually would be a very tedious and error-prone process. We provide 2 high-level user interfaces to automatically generate table entries based on some higher-level commands. First, the user can provide a high-level routing path, which the system will automatically break down in time flow table entries. And the other option is for the user to provide an even higher level routing algorithm. Then the system will automatically apply the algorithm to the network topology and generate paths for all Tor pairs in all time slices in the topology. Concretely, we provide a number of user APIs as a front end in Python. We have routing APIs, such as adding a path to register a path between a source and a destination, or implementing a routing algorithm interfaces for users to implement their own routing algorithms. Of course, topology APIs for users to generate their own topologies based on time, but also on traffic. And APIs to facilitate measurements and testing that provide already built-in telemetry. So from the user view, these are high-level APIs, but one may also wonder how OpenOptics functions as a whole system. So under the hood, OpenOptics takes the front-end Python script written with these APIs, and then uses it in the control plane to generate the topology and the routing, while also initializing possible monitoring. The system will then load the corresponding OpenOptics data plane. The data plane can run on different backends, as said earlier. For a hardware testbed, we support using programmable switches plus optical hardware, but we also support emulation via MiniNet and simulation via NS3. So other than the basic architecture and APIs, OpenOptics also provide more modular services that can be used as building blocks to realize specific optical architectures. But please refer to our paper for more information on these. So all in all, now the question is, how easy can it be to deploy an optical data centers if using OpenOptics? Well, it can be as little as 10 lines of Python code if using, of course, higher level APIs. So now that we established how OpenOptics works, we're going to show how we leverage it to conduct evaluation of optical architectures. So OpenOptics supports different backends. Today, we showcase our testbed evaluation of OpenOptics using physical hardware as a backend. For a comprehensive evaluation, we use 4 2FINO2 switches. The bottom 2 switches emulate 4 Tor switches each. One emulates a microsecond switching optical circuit switch, and the last one serves as a node for the electrical fabric. Finally, we also use a MEMS optical switch to run the millisecond to second scale switching architectures. And this setup allows us to showcase a number of architectures, which in turn allows us to do cross-architectural comparison on the same testbed using some applications. So the figure on the left shows latency of short flows on a MancashD benchmark, while the figure on the right shows a ring or reduced benchmark on the glue communication library. So in the first figure, we show pretty much the effect of different hop counts on latency. So the CDF ends up reflecting the hop count distribution over time of various optical architectures. In the second figure, RotoNet and Opera are using direct path routing. So circuits, in the case of our testbed, which is kind of small, are available half of the time, which makes throughput lower than, for example, traffic-aware architectures that end up using just a ring topology to match the traffic pattern. Another question may be also how loyal our implementation of existing architectures is. In this plot, we show a CDF of end-to-end latency. The curve on the right is from the Realizing RotoNet paper, and the one on the left is our implementation of OpenOptics. And putting absolute values such as intrinsic network latency, which of course different among the 2 physical testbeds, we see that the 2 curves pretty much show the same trend in terms of latency over time, which gives us some confidence in this regard. We can also use OpenOptics to study the performance of upper layer protocols, which are external to the framework. Here, for example, we show an example with TCP congestion control. We run simple hyperflows and then measure network throughput on the left and the instances of packet reordering on the right. What we can take away from this is, for example, that OpenOptics will allow the implementation of VLB routing that simply sprays packets to all DCN nodes and then as they wait there for a direct circuit in traffic-oblivious architectures. But actually, as we can see in the figure, this actually causes extreme disruption to the TCP network stack because of very high packet reordering, which also results in very low throughput, showing that actually if we wanted to run VLBs, maybe on the kernel, you would need an entirely dedicated transport to be even usable. OpenOptics also provides a dashboard included for easy observability, which provides topology visualization for each time slice and metrics such as queue depth over time for different ports and queues. OpenOptics is completely open source. We provide all code and installation scripts on our websites, so please check it out. So OpenOptics' main contributor and maintainer is Yiming, and he would love to hear your feedback. He is also now on the job market for industry jobs, so please reach out to him directly. And if you're interested in using OpenOptics or collaborating or just leaving feedback, please scan the QR codes and reach out to us. We would love to hear your feedback. And this concludes my talk, and I will be happy to take questions.